In this lesson, we will discuss kernel K-means clustering. We will go over some kernel K-means clustering basics, discuss kernel functions, and work out an example. At this point, we have already seen that the standard K-means algorithm works very well when the clusters are linearly separable. However, it struggles when the clusters are non-convex in shape. In this illustration, we have two clusters, the inner cluster and the outer cluster. Notice how K-means failed to separate these two clusters. It was able to identify part of the outer cluster with most of the inner, then the other part of the outer with a few points from the inner. So it's not able to detect clusters that are not linearly separable. The key idea behind kernel K-means is to project the data into a high-dimensional feature space using a kernel function, and then perform K-means clustering in that transformed space. This way, even if the clusters are non-convex in the original space, they may become linearly separable in the kernel space. The procedure is summarized as map data points in the input space into a high-dimensional feature space using a kernel function, perform K-means in that mapped space, but of course, the computational complexity is higher than K-means because now we have to compute and store an n by n kernel matrix, where n is the number of data points. Now, let's go over the most commonly used kernel functions. The first is the polynomial kernel of degree h, defined as the dot product between the features plus 1 all to the power h. This kernel measures similarity not only based on the direct dot product, but also includes higher order feature interactions up to degree h. For example, with a quadratic kernel, we are effectively including all squared and cross product terms of the input features. So it's capable of detecting non-linear boundaries between the clusters. In this example, the original dataset is not linearly separable. However, when we map the data using phi, the mapping function phi, the data is projected into a higher dimensional feature space. In this new space, the previously inseparable points can be divided by a simple linear boundary. The second kernel is the Gaussian radial basis function, or RBF, given by the formula e to the power of the negative of the squared difference between the feature vectors over 2 sigma squared. And this RBF kernel measures similarity based on the distance between the data points. So the closer points will have higher similarity, and it's widely used for detecting nonlinear structures. Finally, the sigmoid kernel, which is defined as k multiplied by the dot product between the features minus delta, originates from the neural network theory, and it can act as a smoothing threshold function. Moving to the formulas, the kernel K-means algorithm is expressed mathematically in terms of the kernel function. First, the formula for the kernel matrix K for any two data points xi, xj that belongs to ck, k of xi, xj equals the dot product between phi xi and phi xj, where phi of x denotes the mapping from the original space to the higher dimensional feature space that we compute through applying the kernel functions in the previous slide. Next, the sum of squared error criterion for the kernel K-means remains as before. However, we replace xi with phi xi, which we don't compute directly, we rely on the kernel functions to obtain these values. So it's important to point that the clustering can be performed without explicitly computing phi xi and phi xj, since all the computations rely on the kernel values, which represent the inner product between phi xi and phi xj. Now, let's work out a concrete example. Suppose we have 5 data points in the original space. Also, we have an RBF kernel with sigma equals to 4. When the value of sigma is small, it means this kernel is sensitive to local changes, whereas a larger value of sigma would smooth things out and treat many points as similar. We apply the formula of the kernel function to calculate the kernel matrix. Then we use these values to compute the sum of squared errors as part of the K-means clustering. To wrap up Kernel K-Means clustering, the original dataset contains circular structures. The standard K-means failed to separate nonlinear shapes. However, once we applied the RBF kernel, the data got mapped into the higher dimensional space, where the two clusters become linearly separable. The red points stayed together with high similarity, and the blue points stayed together with high similarity. And this is how internally the kernel K-means work. It allows discovering these nonlinear structures through linear operations in the transformed feature space. In summary, we discussed kernel K-means.